Welcome to the unit on reaction kinetics. So here are our objectives today. Explain the concept of reaction mechanism, use collision theory to interpret chemical reactions, define activated complex, and then reaction coordinate diagrams. So to start, I want you to consider the reaction between hydrogen gas and gaseous iodine to make gaseous hydrogen iodide. Write the balanced chemical equation. So pause the video and make sure that you can do this. So this is hydrogen gas plus iodine, and I'm saying this is in the gas phase, reacts to form gaseous hydrogen iodide, which is HI gaseous. All right, now I need to balance the equation, which is 2, and I'm done. Hopefully you should have got there pretty easily. All right, so on a molecular level, what must happen for this reaction to occur? What is actually going on when hydrogen reacts with iodine to form hydrogen iodide? Pause the video, think about it for a minute, see if you can come up with 3 things. Okay, so on some level, we know that hydrogen and iodine are compounds that have single bonds. So in order for anything to happen, the single bonds must be broken. So we must, 1, break bonds. Okay, so that would be the HH bond and the II bond. Okay, now the opposite of this is we must make bonds. Okay, and we're going to be making HI bonds. Now, the one that's actually a little tricky is actually it's probably the most obvious of all of them, which is why nobody thinks of it. Okay, think about it this way. If I have my hydrogen molecule on one end of the classroom and iodine on the other end of the classroom, are these two things going to interact? Well, no, of course not. They're too far away. So these two molecules must be close enough so the reactants must get close enough to react. Okay, so kind of more on this later. So now the last thing that I want you to do, and I do want you to try this one on your own again, is to give a series of steps that might occur for this reaction to happen. Okay, pause the video and see if you can come up with a series of steps. Okay, so there are of course many different possibilities, and so I'm just going to give you a couple. All right, let's say I think that the first thing that's going to happen is iodine is going to break apart into 2 iodine atoms. Okay, and I think that the hydrogen gas is going to break apart into 2 hydrogen atoms. And then I think that the last step is going to be 2 hydrogen atoms reacting with 2 iodine atoms to form 2 hydrogen iodide molecules. Okay, maybe you came up with something similar to this. Maybe you came up with something like this. I have my 2 iodines that break up into 2 iodine, or my iodine molecule breaking up into 2 iodine atoms, and then 1 iodine atom reacting with a hydrogen atom to form hydrogen iodide plus hydrogen. Okay, and then I take my iodine, my remaining iodine atom, plus this hydrogen atom that I formed to make the other hydrogen iodide. Okay? Maybe one of these things happens. Who knows? Okay? These are both called reaction mechanisms. Okay, and reaction mechanisms are very difficult to prove or disprove because they happen so fast generally. There are clues that we can use to piece this all together, but for the most part, we're just making educated guesses about the best possible reaction mechanism. Okay, so a reaction mechanism is just a series of steps that might occur in an overall reaction. Okay, so if I look at this equation, all right, and I add these steps up like we did for Hess's law, you'll see that the hydrogens cancel out and the iodines cancel out. Sorry, hydrogen atoms and iodine atoms, and I'm left with the overall equation. That's really what we're looking for. Okay. Now these. Okay, these show up in the steps of a mechanism, but don't show up in the overall. Okay, and we call these intermediates. All right, now I want you to take a look over here. I want you to pause, and I want you to show me where the intermediates are over here. Okay, hopefully you see that the iodine atoms are intermediates, so here's an intermediate, okay, because it gets used up here and here. And the hydrogen atom, the single hydrogen atom, is an intermediate as well. Okay. All right. So here's a sample video that I want us to watch.
A reaction mechanism is a description of the molecular interactions and energy changes that take place during a reaction. The sum of all these changes produces the overall reaction equation. These descriptions usually cannot be determined directly and are therefore theoretical constructs developed using various types of experimental evidence. A good example of a reaction mechanism is the formation of hydrogen iodide. The simplest possible mechanism requires a single collision between a hydrogen molecule and an iodine molecule to form two molecules of hydrogen iodide. However, the true mechanism as theorized from various experiments proves to be much more complicated. Three molecular changes and collisions, creating two intermediate species, atomic iodine and dihydrogen iodide, must occur for this reaction to take place. Each of these steps takes place at a different speed and each has different energy requirements. However, the overall reaction equation remains the same.
Okay, so that's a nice visual of what we've been talking about. All right. So the other thing that we talked about was that the molecules have to come close enough to interact with each other. And this is something called collision theory. So in order for reactions to occur, molecules must collide with each other. That's the simplest way of saying it. I think the book definition gives something like this. Reactant molecules must collide with a favorable orientation and with enough energy to merge the valence electrons and disrupt the bonds of the molecules to form the products. Okay, so let's talk about collision theory a little bit, and let's use this reaction. 2AB forms A2 plus 2B. Okay, so let's look at this first reaction, or this first collision over here. Okay, so I've got two AB molecules coming together. Okay, and they collide, and that collision reacts, or during that collision there's a reaction, and you get a change. Okay, a chemical change, where you form A2 plus 2B atoms. Okay, simple enough. So this works. Yay. Okay, now let's look at this one. This one actually doesn't work. Okay, now you'll see that in order for the reaction to occur, the two A's have to be close to each other. They have to be in proximity to each other in the molecule for a reaction to happen. That makes sense, right? So here, the two A's are close enough to each other, but nothing happens. The things just bounce off each other. Well, that means that there wasn't enough energy. Okay, and we're going to talk about this more in a second. Okay, now in this one, again, there's no reaction. I end up with 2AB at the end. Okay, the problem this time, though, is that the molecules aren't in the correct orientation. All right, so in order for a reaction to occur, you have to collide with enough energy and be in the correct orientation. Now, these seem like they might be prohibitive to reactions occurring, okay? But your energy barrier could be very small, okay? And we're talking about like billions and billions and billions of reactions happen, or collisions happening every second, okay? So, because we're talking about like moles of particles here. We're not talking about single molecule scale, okay? We're talking about moles and moles of particles. So if you imagine having a mole of particles, they should be colliding all the time. And you should end up with enough collisions where the orientation is correct, okay, in order for a reaction to happen. All right, I think a great example of this occurring is NO plus Cl2 reacts to form NaCl plus Cl. Now, here's nitrogen monoxide. Let's say it's a triple bond. Okay, and here's Cl2, a single bond. Now, if the chlorine collides with the nitrogen end of the molecule, nothing happens because we need to make NaCl. Okay? Now, if the chlorines collide with the oxygen, then we can get a reaction. Okay? So this is just an example of molecules having the correct orientation. Okay, so here's that HI example again. So here's my HI molecule, and in order for these things to collide and react, they have to be the H's need to be next to each other and the I's need to be next to each other. You can't do opposites, you can't have weird orientations, okay? It's a single effective orientation. Okay, so the other piece of this besides orientation is energy. You have to have enough energy for collisions to happen. All right? So I want you to pause and I want you to write the reaction for the enthalpy of formation of water. Okay, you should remember how to do this from our thermodynamics chapter. Okay, so what I get here is H2 gas plus 1/2 O2 gas yields H2O liquid. Delta H of formation is negative 285.8 kilojoules per mole. Okay, so this would be enthalpy of formation of water, and I want to, when I'm talking about this in this case, okay, I actually don't want the fraction in, so I'm going to multiply everything by 2. So 2 hydrogens gas plus 1 oxygen gas forms 2 H2O liquid. Delta H for this is going to be 2 times negative 285.8, which is negative 571.6 kilojoules. Okay? And I want you to pause and see if you can remember what that negative sign means. Okay? Hopefully you remember that this means that this reaction is exothermic. Okay? And so here's a memorizer for you. Bond breaking is endothermic, and bond forming is exothermic. Okay? So we're going to use that in a second. I want you to draw an energy diagram for this reaction, okay, this whole reaction here, based on what we learned in the thermochemistry chapter, okay? So pause and see if you can do that. Okay, so here's my axes. This is the reaction progress. Okay, and this is going to be energy in kilojoules. Oops. That messed me up a little bit. Okay. Now you would have drawn something that looks like this. Okay, this is an exothermic reaction, and you know that delta H is negative 571.6 kilojoules. Okay? But based on this, if I took hydrogen, which is in air, and oxygen, which is in air, and I brought them in close proximity to each other, they would react. Okay? Now, for those of you who are astute out there, this is an exothermic reaction that produces a whole lot of heat. So we'd be getting like little explosions all the time. And clearly that is not the case. Okay? So this, as it turns out, is a little bit of an oversimplification. Okay? So let's see what this actually looks like. Okay? I'm going to set it up exactly the same way. Okay, energy in kilojoules. Well, that's a J, kilojoules. All right, so I know it's an exothermic reaction, so I know that I'm going to net lose energy during the reaction. Okay, this reaction releases energy in the form of heat. Okay, but I have to break some bonds first, which means that I have to put some energy in to break these bonds, because there's bond breaking is endothermic and bond forming is exothermic. Okay, so my diagram actually looks more like this. Okay, and this is a reaction coordinate diagram. Whoa, why have you gone all crazy on me? Okay, so this is a reaction coordinate diagram. All right, and there are some features in here that I want to talk about. Okay, so last chapter we did change in enthalpy. Okay, if you looked at that section in the textbook that we didn't actually do, there were some other things called delta S and delta G, which are other forms of energy. This chapter, we're switching from delta H to just delta E to kind of simplify the picture a little bit. All right. So this change from here, from your reactants to your products, this is delta E. Okay. The change in energy of reaction. Okay, now keep in mind I could have delta E forward and I can have delta E reverse. Okay, now hopefully you realize that delta E forward just equals delta E reverse. But there's a negative. Okay, so if delta E, if this is an exothermic process, delta E forward would lose energy, and delta E reverse would be an endothermic process. It would have to gain energy. Okay, so the energy it takes to get over this barrier here, okay, is called the activation energy. Okay, and it's E sub A. Okay, so E sub A is the activation energy. Okay, so if we assume that this process all happens in one step, okay, what would that look like? Okay, I've got two hydrogens and one oxygen. And this is, of course, super unlikely. Okay, this hydrogen's coming this way, this hydrogen's coming this way. They're both going to collide with that oxygen at the same time. And for a brief fraction of a millisecond that doesn't actually exist, I'm going to get something where I'm going to have bonds starting to form between the hydrogens and oxygens, where water is going to come off. Okay, but these hydrogens are still interacting with each other, and the oxygen is still interacting with each other. Okay, so we form this complex, which is very unstable, meaning high energy. E-N-E-R-G-Y, energy. Okay, and this complex has a special name. It's the activated complex. Okay? So, anytime that you have an intermediate where you have bonds breaking and bonds forming at the same time, okay, that's an activated complex. And that would be like the very top of your energy barrier here. Okay, so activated complex. Okay, so the last thing that I want to talk about is this. The energy that it would take to go from your products up to the activated complex. Okay, this is EA prime. And EA prime is the activation energy for the reverse reaction. Okay? So these are reaction coordinate diagrams with kind of everything labeled. Here's another video that kind of shows all this.
The activation energy is the energy put into a system to start a reaction. While many reactions will proceed spontaneously, they still require a small input of energy to start. Matches, for example, burn, but only after energy is added through frictional heating caused by rubbing it on a rough surface. In other reactions, Activation energy may come from heat, light, electricity, or any other energy input to the reaction system. Exothermic reactions require activation energy to start, but eventually release more energy than they consume. The energy given off as the product forms supplies the activation energy needed for the reaction to continue. Endothermic reactions require a great deal more activation energy. Although they also release energy, it is not sufficient to sustain the reaction without continuing to add activation energy.
Okay, so here's a little challenge for you. Okay, I want you to pause. I want you to try to draw and label the energy diagram for an endothermic process. Okay, make sure that you include axis labels. Okay, delta E, the activation energy, and the activation energy for the reverse process, okay, for an endothermic process. So pause it, if you haven't already. Pause it. Try this. Okay, so axis labels. The x-axis is reaction progress, and the y-axis is energy. Whoops, a daisy. Energy, and let's call that kilojoules. Okay, you could do joules, but energy, some unit of energy. All right, now you know that an endothermic requires energy to go, which means that my reactants are here and my products are up here. Okay, so here's my delta E from reactants to products. Okay, I'm still going to have an activated complex, which is going to be higher. It's going to be the highest energy species present. Okay, this from here, from my reactants to the activated complex, is E sub A, the activation energy. And this value from the products to the activated complex, okay, we should probably have labeled that. Activated complex. Is EA prime. Okay? All right. So here's another example. You probably saw this one in the textbook and were a little confused as to what was going on. Okay, so this is our same old reaction, H2 plus I2 yields 2HI. Okay, and if I were to write out the mechanisms that this indicates, I would say I2 yields 2 I's, okay, because this first valley here is H2 plus 2I, which means that this activated complex, okay, is going to be for the breaking of I2. Okay, so it might look something like this. Okay, where the molecules, energy is being put in to start breaking the molecules apart. Okay, now the next step is going to be an I plus HI, or H2, sorry, becomes H2I. So if I look at this, here's my H, here's my other H, and here's my I coming in. This activated complex here, okay, might look something like this. Okay, where this bond is breaking, and these two bonds are forming. Okay, and you're making this H2I compound. All right, and then this last step here is H2I plus I forming 2HI. So there's kind of lots of stuff happening here, right? So I have my let's see, how do I want to draw this? Here's I, here's H, and here's an I coming in. Okay, so this bond is forming, and this bond is breaking. Okay, so this is just going to show that mechanisms can lead. If you have like a multi-step mechanism, you're going to have activated complexes for each of the steps in the mechanism. Okay? All right, now on to some sample problems. What I want you to be able to apply out of here. Draw and label the energy diagram, which is another word for reaction coordinate diagram, for a reaction in which delta E is 30 kilojoules per mole, EA is 40 kilojoules per mole. Place the reactants at energy level 0. Okay, give values of delta E forward, delta E reverse, and EA prime. Okay, so pause it, give it a try, see if you can do this. Okay, so I'm going to start out with my axes. Okay, there's my energy, probably in kilojoules this time, right, or kilojoules per mole, just to make things easier. All right, I'm going to place my reactants at energy level 0. Okay, so the first thing that I'm going to want to do is I'm going to want to try to figure some stuff out. So this looks like it's an endothermic reaction, right, because delta E is positive. So my reactants are going to go at 0. Okay, and my products are going to go higher than that. It's an endothermic process, so this is going to be at 30. Okay, now I probably haven't drawn this to scale. And EA is 40, so I need to go up to 40, okay, to draw my activated complex. All right, so EA is 40, and that'll leave delta E as delta E here. Okay, so delta E forward is just, oh, sorry, that needs to be an F. Delta E forward. Okay, delta E forward is the given, 30 kilojoules per mole. Delta E reverse, okay, would be for the reaction going that way, which would make it exothermic, which would make it negative 30 kilojoules per mole. Okay, the only other thing that I have left is EA prime. So the energy, the activation energy for the reverse process, or from products to activated complex. So this guy right here. Okay, so I'm going to take the peak, 40 kilojoules per mole, minus the products, which is 30 kilojoules per mole. And I'm going to get the difference, which is 10 kilojoules per mole. Okay, easy enough.